Okay, good morning. This is the quiz solution for number one. Yeah, number one is just small piece of writing. Small piece of writing. You see on the right side of the equal sign, it is zero, right? So, what is the Laplace transform of zero? Zero, right? Okay, it is zero. And then when you want to find out what is XS, you reorganize the 5s squared and 2s, right, into this bracket, and then you can express XS equal to something. Because on the right hand side is zero, so XS is also zero. Yeah. Finally, you inverse back zero into time domain. What do you get? Also zero. So nothing happened with the system. Anyone get it right? You get it right? Okay. Yeah. So the first problem is the test of common sense. Okay. Yeah, most likely you are blinded by the difficulty of the ODE. Yeah. Okay. Okay. For number two, let's see for number two. For number two, we have a unit step function as the input. Yeah. Here is unit step function. And then I reduce the complexity from second order to just first order system. Okay. And so we only have here on the right side 6s times xs, which comes from here, 6x dot. And then the 2xs is coming from the 2x. The Laplace transform of step is 1 over s. Unit step 1 over s. No delay at all on the step function. And so we reorganize the equation so that we can express the xs. Yeah. And then you check on the Laplace table the relationship between the 1 over s times s of plus a. Yeah. And this is the inverse. So finally you get into this point. Anyone get it right? Oh, it is okay. 2 over 6 is okay. Yeah. Say that again. Don't you read there is a message in here, right? Time limit 20 minutes, open book and notes. Oh, I don't know. Yeah, it is open book and notes, so you can see also the Laplace table. So the mistake is not on me, it's on you, right? Okay. Okay. Right. Anyone wants to clarify on the steps? Are these okay for all of you? So let's see from the ODE to the Laplace. Yeah, the 6x dot is converted into 6s xs, and then the 2xt is converted into 2xs, and then the ut, this is the unit step, converted into 1 over s. The next step is you organize the xs term so that you take out the xs only, and then you get this term in the bracket, 6s plus 2 in the bracket. Okay. After that, you move the 6s plus 2 to the right hand side. Yeah. It becomes the denominator here. Okay, denominator. After that, what you do? You try to find a Laplace transform pair that match to the format. Okay. Say that again. This one? Your right hand side is 0, right? Yeah, the top one is 0. This top one is 0. From the very beginning, the right hand side is 0. So you move it to the right side, yeah, 0 divided by something. Yeah. Didn't you forget that this is my style of giving problems? Sometimes in statics, dynamics, I give tricky question.
You give the easy one, make it like harder. Like without I like myself doing it.
Yeah, no need Laplace table in here. No need Laplace table. Okay. What do we do from here to here? Anyone know what do we do from this step to this step? Yep. Okay, what I want to do here is that I want to make the variable in front of s to be 1. Okay, so that it matches with the table. So we have to divide by 6. Divide by 6 on the bottom part, divide by 6 on the top part, so we get this. Okay, and then what happened in here from here to here? Anyone know what happened? Yeah. Yeah, why 1/6 is coming out? It's a constant. Yeah, if it is constant, you take it out. The linearity property. And so this part over here is coming from the Laplace inverse. Yeah. So let us see the third one. The third one is you need stuff with delay. So you need some kind of thinking on that. Technicalities lah. That one technicalities, not just common sense, but you need also to know how to handle the delay. Okay. The top part here, instead of 1/s, we have e to the power of minus 5s. Yeah, this part is because of the delay. Okay, and you see this? Yeah, we use the T-shift theorem. If we delay the step function by a, then we get the minus a over there. E to the power of minus a. Then a here is 5. Yeah. Any issue on getting the right hand side equation? No, yeah. You only multiply with the constant of exponential. After that, same thing, you reorganize xs side and then move this to the right side. Move 6s plus 2 to the right side. Okay. What happened after that? Still the same. You find out which Laplace transform pair, yeah, that match with your system. And so this e to the power of minus 5s is a constant. Yeah, that one is a constant that you can take it out. Okay, this one you can take it out. And this one, when you get the Laplace transform, it is just this, yeah. Okay, the e to the power of minus 5s is the one you find here. Meanwhile, the fs is over here. So if I write it on the board, you have Laplace inverse of this one, and then we have the 1/6 . Okay. So you recognize that this is the, and this one is the fs, okay? So when you get it back, this one become ut minus 5. And this one just become f of t minus 5. Okay? That's because of the T-shift theorem. Yeah. So this is the ut minus 5 that we have, and this is the ft minus 5. So the same ft, but the t replace it by t minus 5. You replace it. But by the way, do you know how does the xt look like without delay? Without delay, how does it look like? Exponential function. When t equal to 0, what's the value of xt? When t equal to 0, let's compute. Yeah, let's compute. Let's compute. When t equal to 0, xt is equal to half 1 minus e. This is times 0, yeah. So this is half 1 minus e power of 0, 1, right? So half 1 minus 1, which is 0. So it starts from here. What about as time goes to infinity, what happened with the value xt? If we push t go to infinity, xt will approach what value? It approach half, yeah, correct. Because this part, it will approach 0, okay? Can you see that happen? Yeah, you get half times 1 minus e with a number that is very large in here. This term will become 0. If this term becomes 0, then you only have half in there. Okay, so half is there, so that's what you get. Now what about the delayed one? The delayed one, this one, what will happen? What I should draw? That's correct. Yeah, the same thing, but you, sorry. So this is 5, and then we have the same thing. And the shift is because of two things. The first thing is that you multiply the delayed step, and then you replace t with t minus 5. So it will result in the delay of the response. Okay. There is another way of solving this. There is another way of solving this. Yeah, you see, the input itself is a delayed unit step. Okay, delayed unit step. So what happened is that that we draw it here. At 5 seconds, you get the input. Okay, at 5 seconds. So from what happened from 0 to 5? Nothing happened, right? Yeah, exactly what you see in the first problem. Input is 0 within this time frame. Yeah, from 0 to 5 seconds, there is no input, which is why the output is 0. Okay, and then after 5 seconds, only that you have the step input. Okay, so you write like this. So xt in here is is like a cut function, not piecewise continuous. Yeah. So what do we do here? We don't do anything such that using the T-shift theorem or S-shift theorem. We don't do that. We only say that from 0 to 5, nothing happened, which is why the xt or the response is 0. At 5 seconds, you start giving the step input, and so the response is like that. Okay, so this is using our common sense. Common sense combined with the knowledge of inversing the Laplace transform. Yeah, you can get this. Anything you want to confirm? Okay ya. Yeah, before we go into the convolution integral, if you have any question you want to confirm. Yeah, I'm taking out the convolution integral slides. Yep. Yes, yes. I will return the result. No, no, not that fast. Maybe on Thursday. I will return the result on Thursday. All right. Let's take a deep breath for 30 seconds. 30 seconds, take adjust your breathing before we start the new topic, convolution integral. Okay, ready, everyone? Let's go. This is the slide that I take from your note, yeah, from Wayne's note. The definition for convolution integral starts with the motivation that linearity property is not enough to operate with the Laplace transform. Okay, and then the Laplace transform of product of two function is not the same with the product of the Laplace transform of that two function. They are not the same. Okay, which is why we need a new property, and that is called the convolution integral. Yeah, you see here. Let's say f and g, they are sine function, g is cosine function. You take Laplace transform of the sine times cosine, they are not the same with the Laplace transform of each of them. You take the product. They are not the same. So it is clear that we need a new tool for handling products of the transform. Yeah. And here we come. This is the definition for the convolution integral. We use star here, star, yeah, for the convolution notation. And it is defined as the integral from 0 to t of these two functions, the product of the two functions, you integrate it. Okay. There is a t here and there is a tau. So tau is the temporary term. Yeah, tau is the temporary term, and so the result will be in t. The integral result will be in t time, not in tau. Okay. And this is the property of the convolution. Yeah, commutative, distributive, associative, and then this is the zero element. So what does that thing to do with the Laplace transform then? Okay. So we want to know if, let's say, you have 1 over s over here, and then you have the 5s over s times s plus 1, for example. Or not 5s lah. Let's say 5, just 5. If you want to take the Laplace inverse of this function, but as a product, what you will get? So if you take it as a product, it will result in the convolution integral. That's the motivation, yeah. Although you can also simplify this into, yeah, this is cubic, in cubic, yeah. You find it, you find the Laplace transform pair, you can also solve that without using the convolution integral. You can also do that. So from Laplace table number 17, this is the definition. Okay, Laplace transform of the convolution integral is the product of the Laplace transform itself. Yeah. So let us discuss what is the physical meaning. I want to start from here so that we can have a clear understanding of the convolution integral Laplace transform. Okay, so in the hacker slide, we will also find out several examples to explain what is actually the convolution integral. So you can read that on your own, and I will give another examples to give a clear meaning of the convolution integral. You recognize this? Yeah, spring, damper, this is mass. Okay, and then the mass displacement is x dot is the velocity, x double dot is what? Acceleration, correct. So we give a force in here, and the force could be step, impulse, shock, or any aperiodic function. Yeah, we can get a numerical solution using MATLAB, but we can also get analytical solution using convolution integral. In the several slides from here, I will explain to you how do we get the solution using convolution integral from this problem, not using Laplace transform. Okay. Yeah, you see the function moving from left to the right. The f here is the red box, so the f tau here remains stationary. Yeah, stationary, but then the gt minus tau is the one that is moving. When the two function is coming into, intersection in here, that's when the integral has a value. Okay, and so the result of the convolution integral is the trapezoid, the green trapezoid. That's the result. So how do we use this to solve this problem? Okay, you still remember the impulse? Yeah, the impulse is a very short period force that you give into a system, and the shock duration or the impulse duration is very, very small. And then if you integrate the area under the impulse, the area is 1. Okay, so in this case, simply the height is f, and then the width is delta t, but then f times delta t is 1. Yeah, that is coming from the impulse property. So this is actually a vibration problem, and when you apply an impulse, like you smack it with a hammer, yeah, it is actually acting as a free vibration problem. Yeah, I don't have an example. So after you smack it with a hammer and then you release the hammer, it will vibrate on its own. Okay, which is why it is free vibration problem. And so this is the differential equation from this mass, spring, and damper. Yeah, you have mass, acceleration, damping constant, velocity, and then this is the spring constant. That's the displacement of the mass. Okay, we can derive this using the second Newton's law. And then this is straight taken from the textbook of vibration. Yeah, the result, if you smack it with a hammer like that, this will be the output of the displacement of the mass. Okay, and then x0 and x dot 0, they are the initial conditions. However, because we smack it with a hammer, x0 is clearly 0. Initially, there is no displacement, but because you smack it, there will be initial velocity. Okay, initial velocity. Anyone have a ruler? Can I borrow your ruler? Anyone have a ruler? No? I need to give an illustration. Okay. Let me borrow for a bit, yeah. I hope all of you can see it. So this is the ruler. If I put it here, this one can be modeled as mass, spring, and damper. Okay. So if I pull it here and then I release it, it will vibrate. Yeah. If I do this, that means I give initial displacement. Okay. This is if I give initial displacement. Yeah. I pull and then I release. That's initial displacement. What if I smack it? I give it an impulse. How do I do it to you here? I do it like this. Okay. That's giving an impulse. Okay. So if I do that, that means I give an initial velocity to the system. Okay. So in that case, x0 is 0, but x dot 0 is something. I put it here, yeah. It's okay. So you still remember that impulse is the change of momentum? Impulse is the change of momentum. Momentum is mass times velocity. Okay. Mass is the same. So what changed is the velocity that changed, right? X dot after I give it a smack, and then this is before. Before I give it a smack, it is 0, right? So mx dot is just mx dot after. So which is why, since f delta t is 1 because of the impulse, area under the curve for the impulse is 1. And on the right hand side is just mx dot 0, so x dot 0 is just 1 over m. So we replace 1 over m to here. And then x0 in here and in here, they are 0. After that, we get what we call as the impulse response. Okay, this is called the impulse response. Yeah, the impulse response of the, where is it? It's back again. Okay, let me borrow it again. So the equation that we have here, xt, which is the GT, we call it a GT here, is called as the impulse response. Okay. So let's say if you use a laser to measure the displacement when this thing happen, and then you plot the curve, you will get this. Okay. How does that look like? If we plot this, how is it going to look like? Yeah, it's a sine function. That's correct. That goes smaller, yeah. So I will pull out the constant to the left, and then I have the exponential term here, and then multiply by sine omega dt. At time equal to 0, when t equal to 0, what happened with the system? 0, yeah. So the xt is 0. So after that, it goes like this. Yeah. So this exponential term is the that one. Meanwhile, we have that sinusoid. Okay, the sinusoid. Yeah, that's how it looks like. Okay. Who knows? I need it again, so I put it here. Okay. Now we have the impulse response. At any time, at any point of time, I give unit impulse to this. I get that. Okay. Let's say I give it after 5 seconds. I count now 1, 2, 3, 4, 5. I do that. Then what happened to the plot? Shifted by 5 seconds. That's correct. Let's say 5 seconds is here. It's going to do this. Yep. If I give it tomorrow, not today, it will be delayed by 1 day. Meanwhile, if the magnitude of the impulse is not 1, yeah, the unit impulse magnitude is 1, yeah, but if we give more than 1, we can also do that. Okay, the notation we use here is capital F. Okay, that's the magnitude of the impulse. This is what I said earlier. Yeah, if we delay the impulse by some seconds, this is called tau in here, which you will see the tau also in the convolution integral. Later on, it will show up. Oh, yeah. And so if the delay is tau, and so this will be the impulse response. You see, when it is delayed, we have to replace the t with t minus the delay. And the delay is tau, so it is t minus tau. Yeah, this is the original impulse response. We replace the t with t minus tau. That's it. When we get the delay. Okay. Meanwhile, from 0 to tau is 0. The next question before coming to the convolution integral is that what if we apply the impulse at every time? Every time we apply an impulse. The example is like this, yeah. I do this. So what happened is that I give impulse here, and then there, 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 all the way following this curve. What will happen? What do you think? And then should we add up all of the response? Yes. Yeah, we have to add all of the response. So the response from the first impulse must be added up to the response of the second impulse that I give. Okay. So that's what you will see in here. Yeah. Oh, sorry. So we have a function that is arbitrary. Yeah. Okay. Arbitrary function, and the function in here is ft. Yeah, ft is an arbitrary function, and the tau is just a constant of where I will apply my impulse, and my impulse height will be governed by the ft. For example, at 0, this is the height of my impulse. Meanwhile, at some seconds later, this is the height of my impulse. Okay. After that, in here, this will be the height of my impulse. Then it follows. Okay. And then at time t equal to tau in here, that is the illustration of f tau, and then the delta tau. Okay, this is the impulse that is given to the system. Okay, the impulse given to the system, and then this will be the impulse response of the system. Okay, but this one captures only the response at this point only. Okay, this delta xt is just the impulse response of the system at t equal to tau. Okay, but as we know earlier that at t equal to 0, t equal to 0.1 seconds, there are also other delta xt, and we have to sum sum it sum it all. Okay, all of them we have to add them up. Let me repeat it again. Yeah, the line that you see here is the impulse response of the system at time t equal to tau. If we apply the impulse here, bang, there, then we get the result. Okay, so let's say I apply the impulse here at 3 seconds, so I get this one. Yeah, I get that one. But you imagine that all of this impulse response, I have to add them up from 0 to infinity. I need to add them up. What are they? At t equal to 0, I have to add all of them up. Okay, like for example, in here, yeah, you see how many wave that I have to add them. I have 3 points. Yeah, this one, and that one. So this, and this, there will be the result of the xt itself. Okay, but we have to make a summation from 0 to infinity, or from 0 to t if we want to know only to up to t. Yeah, so if we want to obtain the xt, we have to summing up all of the response. If we only do this, then that's only the response at the time t equal to tau. Okay, okay, that's the motivation. This is the discrete summation. You see, discrete summation. Yeah, like 1 plus 2 plus 3 plus 4. However, as we uh, push the interval close to 0, that is not discrete anymore. It becomes continuous. When it becomes continuous, then we have to do the integral in there, and there's come the convolution integral. So what we can say in here is that the response of the mass displacement is the convolution integral between the arbitrary function that you have and then the unit impulse response. Okay, do you want an example? Yeah, let's see an example. Yeah, let's say we have the same kind of system. Yeah, the mass is 1, spring constant is 2, and then damping constant is 3. This will be the ODE. Yeah, that's the ODE. How do I get x double dot here? Because the mass is 1, 3x dot because the damping constant is 3, 2 times x because spring constant is 2. And then we have the delayed step function as the input, and the height of the step function is 10. Okay, and this is the Laplace transform. We are going to use the impulse response in here. Okay, So if we use the impulse response of the system, that means the right hand side is what? If it is impulse, what will be the right hand side? 1, just 1, yeah. So which is why you get 1 over s squared plus 3s plus 2. Yeah, the right hand side become 1. Yeah. And so because this is a delayed step, split into 2 parts, from 0 to 5 and then from 5 to t. And in here, I already used the the convolution integral. I'm using the convolution integral already. Okay. From 0 to 5, what will be the input? 0. From 5 to t, the input is 10. Okay. The input is 10 flat, 10 flat, yeah. And then this is the impulse response. So we take the Laplace transform. This from xt becomes xs. This is 0, yeah. 0, Laplace transform is 0. And the Laplace transform from here, convolution integral, 10 over s and then g of s. And anyone still don't get this? Yeah? Yeah, because the height of the step is 10. Yeah, let me show it here. The 10 ut minus 5 is like this. Yeah, this is 10 and this is 5 seconds. Okay, this is 10. Yeah, Sean? To get the what? This one? This one? No, no, no. This one is not from here. No, no, not from there. But this one is coming from here. Straight. Let me show you, yeah. The Laplace transform of convolution integral. Okay. The Laplace transform of integral 0 to t f tau gt minus tau. This is equal to fs times gs. Yeah. The f tau in there is 10. Okay. And gt minus tau is our impulse response. Okay. The gs, you put it here. Fs is 10 over s. Okay. Which one? This one? Okay. We are just using the impulse response. So let me remove this one first. So if your system has only impulse input, then your hand side will be, the OD will be like this. Yep, delta T, like this. Which is why this is s squared x of s, 3s. This is 2x. And this is 1, yeah. Laplace transform. And then get s squared plus 3s plus 2, yeah. And this is x of s. This is 1. Okay, so this is s squared plus 3s plus 2. And because this is the impulse response, we call it the GS just now, yeah. That's our GS over there. So in here, we are using the impulse response to obtain the whole response. So we are not using the step response on its own. Okay. So let us continue. If we are using only the standard method, standard method, you go up to here. You have to split into 3 terms using partial fraction, correct? And then after that, each of these terms will be delayed by 5 seconds. You use the T-shift theorem, delay by 5 seconds. Okay, so this A1, you will have a term of e minus 5s later. All of them has a delay. And then what if we use the convolution integral? Let us continue the previous method. This 0 from this is 0 for 0 to 5 seconds. Okay, and then for t greater than 5, you have to take the Laplace inverse of this. This is actually saying the same thing as in here. They are actually saying the same thing. Yeah, 10 over s multiplied by 1 over s squared plus 3s plus 2. Okay, only that the delay term, we don't have it here. Okay, any question so far? Impulse is 1. This one? Yeah, impulse is 1. Unit impulse is always 1. Unit impulse. Unless you multiply with some number, let's say a. So it becomes 1 times a. Okay. There are other examples that I have here in using the convolution integral. Let us discuss one by one, yeah. So we have time, maybe in 5 or 10 more minutes. Another example, if we want to use convolution integral to solve this integral equation. This is called the Volterra integral equation. The second term in here, you notice that this is the convolution integral, yeah, between yt and then sine 2t. We can solve yt in here by first getting the Laplace transform of all of them, yeah. Yt becomes ys, this is ys, yeah, and then Laplace transform of sine 2t, and then this is product, yeah, product of y and then sine 2t Laplace transform because of the convolution integral. Okay, see that one? And then if we solve for the y, we get this. Okay, after expanding, that's what we will get. Okay, so this one is taken straight from the Laplace table. From the Laplace table, that's the solution. So this is how we use the convolution integral. It is also available in the hacker's notes. Any question on this, Michelle? Any issue on this? Where does the convolution integral be used here? It is only from here to here, yeah. Only from here to here, or from here to here. That's where the convolution integral plays role. After that, it's the standard method of inverting the Laplace transform into time domain. You use convolution method if your time domain has this term. Yeah, not the tau, but you have integral of the product of the two function. Yeah, you have integral of the product of two function, then you can use the Laplace transform of convolution integral. Not every case has this. Not every case, yeah. All right. Another example is this. You see, the problem asks us to use these two uh, Laplace transform pair. The first pair is the step, and then the second pair is the exponential function. Okay. What we need to find out is this one 1/s times 1/s minus 1. I have the example just now in here. As I said earlier, we can actually find the answer by just using the, what do we call? Partial fraction. Yeah, partial fraction is sufficient to solve this. How do we use the partial fraction in here? Anyone know? Sorry. Let me erase this one first. You have to find first the coefficient. Yeah, you expand into two terms, a for s, and then plus s minus 1. Yeah, like that. And then after that, multiply left and right by this. Yeah, you multiply by s times s minus 1, left and right. So it become, left hand side become 1. What about the right hand side? And then, okay, if we want to find you use s equal to 0. That's correct. So 1 equal to 0 minus 1 plus b times 0. Correct? A is minus 1. That's correct. Find b. How do we put s? Equal to 1. That's correct. So 1 equal to a times, 1 minus 1. Yeah. 1 minus 1 and then plus b times 1. So as a result, b is equal to 1. So Laplace transform of that, Laplace inverse of 1/s is equal to Laplace transform of this one. Yeah, use that one. So minus 1/s plus 1/s minus 1. Bit easy, right? What about Laplace transform of this? Mi- just minus 1. Yeah, minus ut if you want to call it minus ut lah. What about this? Yeah, it's that one. So it's just e to the power of t minus 1. Yeah, because ut is basically just 1 constant. Yeah. So let's see, if we use convolution integral, that's what we do. Okay. Can you see the answer directly? It's this one, right? The same with this. You can see it, Michael? Clear, yeah? So what happened in here is that you are using the convolution integral property to convert the product of Laplace domain function into integral. Then you solve it in the integral fashion. It is easy because one of the function is just 1. So you just integrate the exponential function. Yeah. Which I also give it here. the same thing. Okay, so you can check it again later in the notes. One more example, or you want to continue next time? This one. Yeah, solving convolution between the two sine function. Yeah, I leave it as a exercise, or do I solve it? I think I solve it here. Okay. So previously, hacker used the integral, yeah, direct integral to solve it. Direct integral to solve it. But then I'm using the Laplace transform. What I need to do here is that I have to recognize that each of the sine function has Laplace transform of this, each of them. Okay, so Laplace of this is actually that one, the product of that one. Yeah, and then what I need to do next is that I have to convert this back into the time domain to get my answer. Okay, yeah, the original equation is the convolution integral, and I need to solve it. But because I take the Laplace transform, I get the product of the two Laplace function. Okay. If I multiply them together, I get this. However, I also find out in the Laplace table that I can match the denominator. Yeah, you see, denominator are the same, but numerator are different. So I have to modify it a bit. Modifying the numerator is easy. Yeah, what we do? Not multiply by 2, but we multiply by 1 over 2 omega. Okay. Yeah, this one is equal to that one multiplied by 1 over 2 omega lah. So 1 over 2 omega will be my constant. Yeah. So what I can do next is just to take this one straight away here and then multiply by my constant. And after that, I arrive at my answer, which is the same as the hacker's answer. Okay. Which one is easier for you? Using Laplace, or you want to do the integral? Yeah. At a glance, it's easier to use the table. So convolution integral Laplace transform method is easier than solving the integral on its own. So there you go. We just prefer the LT Laplace transform of convolution integral with Laplace transform. Yeah, to use to solve the problem. There are other. I think I put other example also here. Yeah, which you can read later. Yeah, you can read later. So I'll see you again on Thursday.